Oh, and we got David. All right.
There you go.
So morning, everybody. And then Damien, you're on the email chain though, right? At least, so you got the link.
Yeah, I got the link right now. Well, no, I got that you sent me the password, but I didn't get the link in the email chain. Had you sent it before?
I meant
I
the.
just opened it up in Canvas again. I just went to the class and found your meeting like that.
Oh, got you. Okay, I need to add you to the list because there's already a folder of recordings from last time.
All right, great. Thank you.
Yep. Okay, so kind of quick recap from last time. So let's do a quick recap. We identified kind of important things that we wanted to be tracking in our cell. So like kind of important model parameters that we were looking at, right? And so things we were looking at most were voltages, currents. That helped us get power and energies, right, that were useful for our cell. So those are kind of the high level, at least kind of the high level system level stuff that we were looking for. And we started by, all right, well, what's the voltage under equilibrium, right? And that got us to the Nernst equation, right? So we said we had some voltage was equal to some standard voltage. So this little naught just means it's at standard conditions. Right, and we got some term, this RT over NF, natural log, and we have a term for kind of the, we'll go more into the detail of these terms because it's more complicated, but it's basically a term that kind of has all the activities, which could either be like concentrations or pressures of your reactants over the concentration of your products, which will be important. And we also determined that our standard voltage we could get from change in Gibbs free energy, right, at those conditions, divided by the charge associated with the half reaction and Faraday's constant. So that was kind of the way that got us in the ballpark. And the last thing is we said, if you wanted to kind of, let's say you wanted to make a gasoline fuel cell, right? Like, we burn hydrogen, you could burn gasoline, we burn methanol, all this stuff. And when I say burn, I mean kind of oxidize. So we oxidize this stuff, and you could methanol in fuel cells. You could think about, well, what would be the voltage if I made a gasoline fuel cell, right? And so you could look up what's the change in enthalpy minus temperature times the change in entropy, right? Get you the Gibbs free energy and could get you the voltage of your system. So that's kind of relating it to some kind of common thermodynamic properties. So I want to look at real kind of a system where the reactants are not continually supplied and the products are not continually removed. So like, and the case where that does happen is a fuel cell, right? So a fuel cell, we've been talking about hydrogen continually gets supplied, oxygen continually gets supplied, and water continually gets removed, right? And so that's kind of a special subset that actually most of us don't work with. It's an easier subset to handle because things don't change with time. It kind of runs at steady state, but pretty much all of our stuff will change with time. So let's kind of do our first dive into kind of trying to predict the performance of something that changes with time. So let's look at electrochemical system. Right, so this is like an electrochemical cell, right? right? So like in your cell, you might just have a certain amount of reactants, right? And you're just gonna start, doing an experiment, and you're gonna start consuming reactants and creating products. This is also true in a flow battery. Like you are in the flow battery case, you are kind of refreshing things at the surface, but in whole, your whole system is changing its concentrations from one side to the other. Or this is also true just in a typical battery, right? I mean, so as you basically these are things that you discharge. And I want to look at, so let's look at, maybe there's probably two really common flow battery technologies that are out there. One's vanadium and one's iron chrome. So I'm gonna look at iron chrome since it's a little bit of a simpler system. So this iron chrome flow battery, so you have on one side, you have this, you're gonna start off with a bunch of chromium 2 plus, and it's gonna have acid. So some H2SO4, let's say, like some sulfuric acid. I'm not sure actually if that's the acid you'd use with that. You might use like hydrochloric acid or something, but sulfuric acid is a pretty common one in flow batteries. Here you'd have a proton conductor sitting between them. And then on this side, you'd start off with some iron 3 plus and some H2SO4. Right? And you imagine you could either just have tanks sitting next to the reaction sites, or you could have tanks that pump stuff and flow stuff through. So this works for either one. And then let's envision we have, and then you're going to have usually kind of a porous conductive layer or a catalyst here. So this would be like kind of your, they might not call it a GDL. Last time we were talking about gas diffusion layers, because these would be liquids, right? So, but we'll call these just our electrodes for simplicity. But typically they'd probably be some sort of carbon felt, and with a catalyst on them is what they'd be in a real system. So kind of what we talked about last time, right? Like if you want to do any analysis on your electrochemical system, the first thing you need to know is what are the reactions occurring at both electrodes. If you don't know that, you're dead in the water, right? So in this case, on the negative side, we have this chromium 2 plus, and when it discharges, it's going to lose an electron, and it's going to become chromium 3 plus an electron. And on the positive side, you're going to have iron 3 plus, and when it discharges, it's going to, when the system discharges, it's going to gain an electron, and it's going to go to iron 2 plus. So if you see the net reaction, right? So we add these two reactions together, we'll see that electrons on both sides cancel. So the full reaction, RXN is kind of like shorthand for reaction. So you have chromium 2 plus on the left plus iron 3 plus, and that goes to chromium 3 plus iron 2 plus. This is our net reaction. So right, if we want to find the voltage, we need the Gibbs free energy of this system. But we're typically not gonna do that. For most electrochemical systems, if you're with kind of common reactants, like gasoline is not going to be something. Gasoline you'd have to go look up thermodynamic properties for, or if you're going to do some different hydrocarbon in the fuel cell, you might have to go look up thermodynamic properties. But for a lot of stuff, the first thing you're going to check is the electrochemical series. So I don't even have one up right now, but let's just type in electrochemical series. I don't know why. I should have a better one like readily available, but it's summer after all. Give me a little break. So here's the electrochemical series, right? And what this does is you can see it gives a voltage right here, and it writes all the reactions as reduction reactions. So most electrochemists are going to write the electrochemical series as reduction reactions. Although this is not, if you go and take the FE exam, they're going to give you a table of with oxidations, which I've never seen in electrochemistry. So I don't even know where they came up with using it, but I'm sure there's other places that do the opposite. And you need to find you'll need to find the two half reactions, right? And you'll notice here that they're all referenced. The 0 point is this hydrogen. So we talked about that a little bit last time, right? This is kind of the reference reaction. So I'm just going to take this. Just bring this over into our. I'm not sure if I see chromium on this yet. Might need to. So what I would look for is kind of the chromium 2+, 3+, redox potential. Right, and so we might have to, let's see if we can find some images to see if we can find it. So this is what I would have to do. So yeah, I would probably find a paper, but for the sake of time, looking for a paper, I want to see something a little more reliable than that. Let's see here. Let's just try chromium redox potential. If someone finds it before me, let me know. Well, maybe Google's got a better one. So it's not going to be this low. Syria. Here we go. Oh, here's chromium, but but keep in mind that this is not the reaction we want, right? So this is chromium 3+ to chromium solid. So we want this one right here. Chromium 3+ to chromium 2+, so negative 0.42. And I'm going to come and I'm always going to check to make sure the 0 point is the hydrogen on their scale. So remember this one. So we got negative 0.42. So that one's not on here. So we have to add chromium. Let's see here. It was chromium 3+ plus an electron going to chromium 2+, which was negative 0.42. All right. And so now that we've kind of rounded out our table, we would kind of look, all right, so the iron, so we have the iron 3+ to iron 2+ at 0.77. So this one would be voltage is equal to 0.77. And this one, we said the voltage was equal to negative 0.42. So in this case, what we're going to do is for the full cell, we're going to subtract the positive from the negative reaction, right? And so that's going to give us a 1 point. So the voltage of the cell will be 1.19. And this will be, and so maybe I'll use the notation I'm going to keep using. Actually, sorry about that. So I would call this like E naught on the negative electrode. This would be E naught on the positive electrode, and this would be E naught. Right. So the standard potential for this is 1.19. So there's a lot of like physics behind this table actually. I mean, you'll notice that stuff up on the top right of the periodic table is typically going to have higher redox potentials, right? Like fluorine has the highest, which basically means if this number's like really high, what that basically means is that this reaction wants to go left, right? And by the way, I cut off a 2+ here. so like if this number is really high, that means it wants to go left. So this means it's a strong, strong oxidizing oxidizing agent. Where here, this means it's a strong reducing agent. So the way you can think about that is like lithium, for example, it really wants to go to the right on this reaction. And so that means it really wants to give its electron to something and reduce it, right? So that's why this is a strong reducing agent. This is a strong oxidizing reaction. This really wants to go this way and wants to take 2 electrons from something to do this reaction. And so we can spend a little time later talking about electronegativities and fundamental nuclear charge, or effective nuclear charge, because those will give you a lot of insights into like why do these elements behave in this way. But it has a lot to do with with their electronic structure, right? And for example, lithium and sodium, right? They're on the far left of the periodic table. Periodic table. No. Right, so like these elements over here, right, they really want to lose, well, I mean, most of the stuff on this side, they want to lose their kind of first 1 or 2 electrons, right? So these ones typically are going to want to lose 1, these ones are typically going to want to use 2, right? So these ones will typically want to lose 1 electron, these ones will typically want to lose 2 electrons. These ones will want to gain 1 electron. You'll see, and these ones will want to gain 2, right? So, and you can kind of, hopefully this isn't the first time you've been thinking about this on the periodic table. And what you'll also see is as you go to the right here, so as you go from left to right, what you're going to do is you're going to add, so this adds charge in the nucleus. So this has added charge in nucleus. Right? And so what you're going to see is those valence electrons will be held tighter. So it pulls harder on valence electrons. And so that's why you'll see as you go down to the, as you go from left to right, you're typically going to have stuff that will, it's going to get smaller. So things will be smaller. Going to be smaller. Sorry, that's not super obvious when I'm writing on top of it. So you go this direction, they're going to be smaller. They're going to be less polarizable. So they're going to be like harder to change the shape of the atom. Right. And then as you go this way, right, they're going to get, in these cases, they're going to get smaller, right? Just because they have much fewer electrons in their electronic cloud, right? And then you're going to get more polarizable this direction. Right. So that's why you'll see like, HI is actually a pretty strong acid actually. And so, and typically, so the way that affects electronegativity is that typically these atoms, so so this is be larger electronegativity. And I'm just kind of mentioning this briefly as something, and we could talk more about this in detail. So things are typically, as you go in this direction across the periodic table, things are gonna be more electronegative in general. So they're gonna pull harder. They're gonna pull harder on those electrons as you go up into the right. And then these elements down here, they have one electron sitting way out from them, so that it's pretty easy to lose those. So you'll see that trend, like so of course the things really low down here that really want to give up an electron, right, are everything on this left hand side of the periodic table, right? So you're going to see lithium, you're going to see sodium, see magnesium, and magnesium's 2+. You'll see aluminum is actually interesting because you can also visualize aluminum as being here, like kind of aluminum 3+ a little bit, right? If you get rid of this D block, so if you get rid of the D block in here, you can also visualize aluminum kind of in this spot right here. Oops. Here, one sec, I gotta reconnect. Go, computer, go. My work computer sometimes goes on the fritz on me, decides just to drop its internet connection. So kind of to keep going, so I was talking about just kind of looking at the, obviously this, keep in mind, this chromium is not in the right place. It should be buried down in here, right? But so like you imagine these lithium, sodium, magnesium, right? They're all down here on the left. And this lithium and sodium want to lose 1 electron. Magnesium wants to lose 2. Aluminum, if you don't look at if you remove the D block electrons, you can see it's actually wants to lose 3 electrons. So you can tell, so these are kind of on the more electronegative end. And then you'll see on the very kind of electropositive end, you have stuff that's up in the top right. So what you'll have is, you have things with fluorine, things where oxygen is being reduced, things where chlorine are going to be reduced, right? So you have, chlorine here. Let's see here. So this is where oxygen reduction, and here's fluorine reduction, right? So as you kind of suspect, those are kind of all up there. And keep in mind, look, here's a chromium compound, right? Obviously the redox potential of this chromium compound is very different. So don't just assume that just because it has chromium in it, it's going to have the same redox potential. So I know there's a lot, but we can talk about it. And I think I like thinking about these kind of trends. And I think thinking about kind of the effect of nuclear charge is a pretty powerful tool to think about in conjunction with just the overall size of the atom, where you can kind of rationalize a lot of these different things. So let's go back to our case, right? So we're trying to model this full cell system, right? This chromium 2+ and chromium 3+. And so, the way you can also kind of think about this is that in this case, this reaction right here very much wants to go to the right. So let's say if you had this chromium 2+, 2, let's write them both as, I'm going to write them both as reduction reactions. So you have chromium 3+ plus an electron going to chromium 2+. So this is kind of a little bit of an aside into the chemical nature of these compounds that causes them to have these redox potentials, because I don't want these redox potentials just to be random numbers to you. I mean, when you see them, you should kind of understand why they lie in these certain areas, because only then will you be able to go, okay, well, if I do this to the compound, or if I switch it out with this, I'm going to see this trend. iron going into chromium. That would be cool. We got like a nuclear reaction going on, going into iron 2 plus. So in this case, on relative to the top reaction, this is more stable, and this is less stable. Keep in mind, so these are relative to these two. And in this case, this is this chromium. This chromium 3 plus is more stable, and this chromium 2 plus is less stable compared to these ones. So one way you can think about this is, so these electrons right here, right? Those are doing a lot. Those are associated with a lot of the voltage you're going to see in the cell. It's not completely a function of this, but the one way you can think about this is basically like you have this chromium sitting right here, right? And maybe it has, it's going to have more valence like electron shells. But we're trying to draw some orbitals, and this is basically like the iron. And so one way you kind of think about this is, so they both have, maybe this right here. And so if we fill these two orbitals up, let's say they would be neutral, right? And so because right now they're both missing 3 electrons, they're in the 3 plus state. So to start to charge state, you have an electron sitting here. But this electron sitting here, it sees this iron on the other side, and it's like, man, wouldn't it be good to be at this much lower of an energy? Like this is my energy. It can reduce its energy by a lot, right? So what you're basically doing in the cell is you're moving this one electron from a chromium, kind of a chromium d orbital, into an iron d orbital. So if you're able to, like, if you're really interested into chemistry and material science, you could, of course, figure out what are kind of these orbital energies, and you could learn a lot about what are the voltages of the cell, right? And so that's, a lot of people do that in electrochemistry, is they try and connect these fundamental orbital energies to electrochemical performance. And so you can think about this as just like that electron is just like it's like water, and you're just, or a mass, and when you want to discharge, you let the mass go down the hill, right? And you capture the energy. When you charge it, you got to push that. When you charge it, you got to push it back up, right? And you got to put energy in, and then when you want to discharge it, you let it come back down. So you're basically just moving an electron from a high energy state to a low energy state. Okay, so that's a little bit about how you can think about where that voltage comes from. But that wasn't too bad, right? I could get a kind of standard potential for this cell pretty easily. But we're gonna say, but we're discharging it, right, Chris? Like, it's gonna start like this, but pretty soon I'm gonna have a bunch of chromium 3 plus, and I'm gonna have a bunch of iron 2 plus, right? It doesn't look like it's changing the way the cell looks. So you're right. So if we write this redox potential, so if we write redox potential E is equal to the standard redox potential plus RT over NF, natural log of the concentration of our reactants. So let's say we have chromium 2 plus, and then we have iron 3 plus, those are our reactants, over our chromium 3 plus times our iron 2 plus. That's going to give us our actual cell voltage. Okay, so roughly most flow batteries, they're going to have a concentration around like 1 to, the best I would hope for in my, if I'm designing cells, if I can report 5 molar, I'd be really happy. But let's say let's say we start off with 1 molar of both of these. So that means we have 1 mole per liter of solution. Right, so that's what 1 molar means, right? And so that's what these concentrations are. So you might think about, what's the state of charge, right? So in this battery, sorry, I'm pumping around a lot. So in this battery, if you have all chromium 2 plus and all chromium 3 plus, your battery's fully charged. If you end up with a cell that has all chromium 3 plus, right, and then on this side all iron 2 plus, your cell's completely discharged. You have all the electrons are all down in here in the iron. There's no more energy to take out of this sucker. so that's completely discharged, right? So what we're going to say is that our state of charge of our system, you could do this for a flow battery, you could do this for a regular battery. It's going to be equal to the concentration of chromium 2 plus over the initial concentration, which that was 1 molar, right, in our system. So if you could track the concentration of chromium 2 plus, you could figure out what's the state of charge of your battery. And you could do the same thing for iron 3 plus. Those go together, right? Anytime you lose a chromium 2 plus ion, you're gonna lose an iron 3 plus, right? Because you're giving the electron from one to the other. So those two are gonna go together. And what you're also gonna see is that the state of charge, you could also say it's the initial concentration minus the chromium 3 plus concentration over the initial concentration, right? And so, for example, so if this was 0 at the start, your state of charge is 1, so 100% basically. But then as this chromium 3 plus gets completely turned, or all the chromium 2 plus goes to chromium 3 plus, you'll see this will go to 0. So you also have the same thing with the iron 2 plus. You have your initial concentration times iron 2 plus over the initial concentration. So I want to put this equation in terms of what we'll call SOC, the state of charge. And so I can see that chromium 2 plus concentration is equal to the SOC times the initial concentration. The iron 3 plus is equal to the state of charge times the initial concentration. The iron 2 plus, I kind of skipped one, but you'll see they're the same. I have to multiply this over. So I multiply that over, right? And then I have to subtract this over. Then this gets subtracted over on the other side, and then I multiply by negative 1. So what I'm gonna end up with is I'm gonna get the initial times the state of charge times this concentration, and it's the same. And it's the same for the chromium 3 plus. And so we can pull out the initial concentration and just say 1 minus state of charge. So this shouldn't look so surprising, right? And so what I'm going to do is I'm going to plug these into my E naught equation. So I have E is equal to the standard redox potential plus RT over NF, natural log. And what I'm going to have is I'm going to have two state of charges on the top, right? The iron 2 plus and the iron 3 plus. So I'll have the state of charge squared over 1 minus the state of charge squared. So let's try that. Let's see if we can figure that out, and let's see if we can predict the voltage versus state of charge curve for the battery. So let's fire up MATLAB. I'm gonna have to do my global protect thing. And just stop me and ask questions on any of this stuff, folks. Give it 2 weeks, and I'm not going to be doing anything. You're just going to be coming in here with your models. So you could also do this in Excel. Oops. All right, so I'm going to make a new script, right? So we're going to close all the windows, and clear all our variables. So this is going to be our low battery model. Right, so N in this case is 1, it's just 1 electron. F is 96485, that's Faraday's constant, right? Which is, and that's in coulombs per mole. Our E naught is 1.19. So you can find the Gibbs, changing Gibbs free energy of that reaction now, if you wanted. And we need to make a state of charge vector. So SOC is going to be equal to, what do you write here? Like a vector from 0 by 0.1, 1. To remember some of my syntax on this. Let's run that. Let's make sure. It asks me to save it. Okay, so it looks good. So this syntax basically made a vector that looks like, made a vector that's 0, 0.1, and 1. So it looks good. And so there's two ways we could do this. You could do a for loop. We could say for some dynamic variable I equals 1 to 10. We could say that E is equal to, we need R and T. So R is 8314. What is this in joules per mole Kelvin, and T we'll say is 298 Kelvin. So E is going to be equal to E naught plus, and you're going to, in electrochemistry, you're going to see this R times T divided by NF all the time. N times F. It's just a really common constant because of the Nernst equation here. And just also the, yeah, I guess mostly for that reason. RT over NF times natural log of, and here we're going to have like SOC of I, this term squared, divided by 1 minus SOC of I squared. We end the for loop, and then let's do a little plotting. So we could plot, and this will have to be E of I, because we'll have to update it. So here we can plot our voltage as a function of our SOC. So that's the command for plotting in MATLAB. So let's see if I got any errors. This is on 14. Maybe I have a mismatch parentheses. So I have this. I don't know if ln is the natural log in MATLAB. So if I ever go to my trusty Google, almost know what natural log is in MATLAB. Well, it should be ln x. Okay. That's not our issue. E naught r times t. We're missing one here. There we go. So if you go across a parentheses in MATLAB, you can see which one it matches up with. No, it doesn't like ln.
Debugging is the best, huh?
Yeah. What is natural logarithm in? Let's see here. It might just be log. I think log is, and then maybe you have to do log base 10. Oh, log.
Wait, didn't they do natural log too right there?
Yeah, it's just log is the natural logarithm and then you have to say log 10 for the base 10. All right, so let's see here. Oh, so instead of 1 to 10, we have to go from so our SOC is 11 long. So we have to go from I equals 1 to the length. So I'll say length of SOC. So it'll just figure out how long is the state of charge, and I'll do it for all those. All right, so it looks like we have some more debugging to do, right? Because it looks like our voltage is like around 40. And so my immediate thought is to figure out what is this RT over NF, right? So this is just kind of RT divided by N divided by F, right? So 25. So this is too large. So this should be 8.314. So this should be, so now it's good. There we go. So now you can see, so look, so you can already see predict. So when you're fully charged, you should expect this battery to be, did I go? So does it not? Doesn't do 0, huh? No, it does 0. I don't know why it's not plotting. Maybe the E naught might not be. Let's see what our voltages are. So yeah, it's undefined at 0 and at the full state of charge. So that's why it's not plotting it. But you can see, so as you charge, you increase the battery voltage, right? And so you could do this for any of your systems if you kind of knew, okay, this is the starting concentrations, and then as they get depleted, they would go in this direction, right? And so let's try a couple of things. So this isn't really a good way to write the code, because let's say we want to do a lot more data points. Let's start off with not that many. So let's see we want to do this many data points. So it's still pretty fast, I guess. We'll compare it though. So now it's probably too slow. So it really, like this, like, all right, I'm just do Control C. That was Control C. Let's see here. Oh, I think I broke it.
So if you're not going to use a matrix, right? Because that's going to be like however many millions of lines. How are you going to do it?
I'll show you. So you can see, so now I did so many lines, it did so many calculations, it's just even having trouble breaking out. Copy. Pull up again. Oh, can I give me another warning? Yeah. I didn't even like to do that one. So you can see, like, it's not a very efficient way to write that pretty simple code, because even as you want to do a lot of, you have to do like a lot of iterations. Right, so we want to go to this depth. It takes a lot of iterations. So let's see here. This was 1, 2, 3, 4, 5, 6, 7, right? 8 if we move it all the way across the 1. This is 1 e to the negative 8. So let's do 1 e to the negative 5. And just look at the results for this for fun. So you can see you have this relatively sloping behavior, and then comes up here at 1. And this is actually, so if you look at this is like, if you look at any discharge curve for a battery, this is mostly the reason why you're going to get this discharge curve. So let's do like, right? So this is so if you look at, let's look at some different lithium battery discharge curves, right? So you're going to have this kind of behavior where you come around the equilibrium voltage and then it dies down, right? So this is the typical behavior you're going to have. And there's some ways to make it flatter. So this lithium iron phosphate battery, it's interesting in that, so like lithium iron phosphate, so you have some batteries, some like lithium ion batteries, where so all of them will have like usually like some lithiated carbon on one side, and then some, this one might be lithium cobalt oxide. And when this one lithiates, it just lithiates randomly all over. And so it just goes from cobalt oxide to lithium cobalt oxide, right? And it just depends on how much lithium you have. But this lithium iron phosphate actually battery is interesting, because what it'll do, lithium iron phosphate, what it'll do is it'll actually lithiate in areas. And so it actually doesn't form one phase, it forms like several phases. And so what you'll see because of that, you don't have this change in concentration. Wherever it reacts, it's always all iron phosphate. So this is all iron phosphate. So the reaction site's always iron phosphate. And you have these just kind of lithium iron phosphate pockets that are now dead, right? And so like you'll see for a lithium iron phosphate, it'll have a much flatter curve. So this one, when you discharge it, this one will kind of come, it'll go really flat and then come back down. But this one will have a more slopey curve. And that's because this has a single phase reaction, single phase. This is two phases. Right. So we're able to kind of capture, pretty easily we can capture this one line, and then around its equilibrium voltage. So but then we want to talk a little bit about running the code more efficiently. So typically you don't want to run this, you probably wouldn't want to run it like this. You could just, MATLAB is pretty efficient at handling vectors. So we just got to figure out how to make it work. Like this one, and this one might particularly be hard. I don't even know if we can, but what the heck, let's give it a shot. because you have to take the log of a vector. So let's take this equation, and instead of looping through all the different states of charge, let's just see what happens when we do SC of I, and I'm going to comment this out. Right. So we don't need the I's anymore.
So what are we doing right now?
So we're doing the exact same calculation, but we're not going to loop through. Right before, right, we basically, to calculate the voltage, we looped through and we gave it a different state of charge at every step and calculated a new voltage. This time I just want to do it in one step. I want to do some matrix algebra, basically do matrix algebra, and just have it figure out, in terms of putting in this matrix into this equation, getting my E matrix, right? Because E is just this long 1,000 row vector, basically, right?
Okay.
So, and this is a much better way, if you can get to do it in MATLAB, to do it this way rather than these for loops. But you're going to see incorrect dimensions, right? So, for example, it wants to do a dot, right, before it raises it to the power. Oh, I also made a mistake here. So look at this, because this is 1 minus SOC, and it's squared out here. We'll check what that looks like, right? Because that whole term should be squared, not just the. Now we have 1 minus our SOC squared, and then this whole term. Right, that looks good. So let's try it. This rudimentary test doesn't seem like doing the matrix algebra is all that much faster, unless it's just going to crash again. It'd be funny if this way is actually slower. So let's start off with a smaller. Let's do 3. Just make sure it actually runs. Why are you not running right now? Oh, there it goes. I'm gonna try running it one more time.
I think you need another dot before the division sign.
Is that what's going to confuse it?
Yeah, I think so.
Surprised it's not spitting out an arrow though, you know?
Yeah, it didn't for me either. I don't know. I think maybe because you can actually do matrix division on those sizes, but it doesn't make sense.
Yeah. MATLAB's been a little buggy today. I'm pushing my little computer too hard. That's one of the things. Probably don't do like a bunch of Zoom videos while you're trying to do these computations. Especially if you have a tiny little laptop. Come on. It's gonna be annoying because I have these like weird weird passwords I have to use to like get into the back end of the computer. That's interesting. I don't know what it thinks it's gonna run that file with. Was anyone able to get to run it in one line? Figure out a way to do it?
Yeah, it worked for me.
It worked for you. Just put with the dot.
Yeah.
Could you compare the two? Was one faster than the other?
Yeah, I think it was faster this way, the vector.
Yeah. At least that's what I was trying to show. Maybe I shouldn't. maybe while I'm doing the Zoom video, maybe I shouldn't try and push it too hard. But anyway, so there's two ways just to do this simple calculation. And so when I would say when you can, the leaning should be to do it this way in MATLAB, is to try and do it in one line of code if you can, rather than try and do the for loops. Especially once you start to having like nested for loops, then it can really take a long time. But you'll notice to do some of these like element by element stuff, you have to put some dots in there. But okay, so we basically found so far, we found that our voltage as a function of our state of charge, right? Or you could say this is equal to our like concentration of chromium 2 plus, or our concentration of iron 3 plus, right? So we could also just plot it as a function of those. And it was equal to well, we'd actually have to, yeah, so that looked like this. And this was our right? And so some interesting things to kind of point out about this is that so in terms of the state of charge, you might be curious, like how much actual charge is that? And so if we, so first we should talk a little bit now about Faraday's law. It's kind of one of the other kind of electrochemical principles we're going to use all the time. And so this basically is just kind of being able to relate charge to moles. So it's basically using Faraday's constant. But you could say that the amount of charge is going to be equal to the number of moles, right? Which you could either put moles or you could put mass over molecular weight. So mass, here's molecular weight, right? Times the amount of charge on each individual particle times Faraday's constant. And sometimes what'll be done is you'll say, okay, well, let's, if I is the current is the amount of charge per time, sometimes you'll see this written as like mass NF over molecular weight times change in time. So you'll see it like that sometimes. So for this cell, we don't need to worry about weight so much, but we can say that, all right, so we must have some Q is equal to the number of moles that we have, right? Times N times F in our system. And so we're going to do this on a per volume basis, like how much charge per volume, because we could add more volume and get more charge. So we'll typically do this on a per volume basis. You'll see here, you have this moles per volume. So that's going to be your concentration. So your initial concentration, CI, we just wrote that as CI. So you have your concentration times N times F, right? And if you, at this point, you could get roughly what's the energy density of the cell, right? You could integrate, you'd say, all right, the energy density, right? And so sometimes in this class, maybe we'll call this like Q hat, like it's kind of like specific to volume, right? So the energy specific to volume will be equal to the integral of the voltage times this. But you basically have this curve, right? You can, instead of state of charge, you could just put in Ci and F here, and that'll be your kind of specific charge, right? And sometimes you probably on a battery, you're not going to operate between 100% SOC to 0%. Most systems you'll probably operate, with some bounds, maybe like, 20% to 80%. Right, so you operate within these bounds. So you basically get the energy density by integrating this portion of it. Right. So that's not. So let's see if we can estimate our energy density for this cell. So so our Q is going to be equal to, we said 1 mole per liter, right? Times N times F, right? And so what we need to do is, you imagine right now we have this data, but it's all discretized. Right? So what we'll need to do is, for each voltage, we'll need to multiply it by this do like a little left-hand side integration, right? And we'll just multiply it by the height over the little delta state of charge, right? And then we're just gonna have to multiply the whole thing by our Q. So let's see here. So we have our E, our energy density, is going to be equal to, what do I do? So sometimes I'll just test something. I'll do sum, see if sum is a thing. 1, 2, 3. Right, so did you mean, I forgot a parentheses. So sum will work. So we could do, this is going to be equal to the sum of the vector E, right? So we'll add up all of E, right? So we'll have each one, and each one of those things should be multiplied by, we'll call this our del SOC. So we have 1 e to the negative 3. And so this would be our del SOC. So this will be multiplied by our del SOC times our Q. And this, so our Q is going to be in units of coulombs per liter, right? And so this one, we're going to have volts times coulombs. So we're going to get joules. So this one's going to be in joules per liter.
Professor, is it going to be case sensitive when you're calling out del SOC?
It will be case sensitive. Thank you. Good catch. And that's not a G, that's a Q. Yeah, so yeah, that's a good point. MATLAB is case sensitive. So let's just give this a shot. So now we have this. Then we have our, ENAN, that's not good. So we got to see what happened here. So our Q is 96485. So what might have happened is that our E has, what I'm guessing is our E has zeros at the first and last. So what we'll have to do, so I mean, a lot of programming is actually just trying to be creative and figure it out what to do. So it has 2 unknown infinite bounds, so we want to avoid those. So we're going to go from 2, the entry 2, all the way to the length of E, so its own length minus 1. So what I'm basically saying here, is I want to take the vector E and sum up every one of it, all 1001 entries, but I'm going to start at the second entry and I'm going to go to the 1001 minus 1 entry. And so what I'm basically trying to avoid in this case is this negative infinity here and this infinity here. So let's try running that again. See if that'll give us a, see if I see this. So here we go. We got 1.147 e to the negative 5. And so if we want to convert this to something a little bit more useful, so let's say you have a joule, right? And so typically what you're going to convert this into, and so a joule is going to be a watt second, because a watt's a joule per second. And so if you multiply this by, divide this by 3,600 seconds per hour, it'll get you watt hours. So if we divide this by 3,600, we're going to get watt hours, which is a more common unit for at least in the battery world. And this is going to be per liter still. So now this is going to be watt hour per liter. Right, so we got about 30 watt hours per liter. Okay, that's not bad. So we could do 31 watts for 1 hour for every liter of solution. Right, so okay, so I think we got a little bit of. So we're gonna jump into real cells here. So this was all equilibrium stuff still, right? So this is kind of assuming we're running the cell slowly. But you can see if, most of the time you don't want to run with huge losses, and so running near equilibrium gives you a lot. I mean, this could also be useful for an electrochemical experiment, or maybe you're depleting. You want to track the voltage as a function of the concentrations of your reactants over your products, right? And so it can help you predict at least the equilibrium voltage, because you're going to need the equilibrium voltage. It's kind of the first step. So let's talk about losses in electrochemical systems. So the way we usually think about electrochemical systems is we usually think about losses in terms of losses in voltage. And so like you saw, like, all right, so this change in Gibbs free energy at standard conditions, this is like the most work that can be done in these systems, right? And so basically this E naught is when the system is running. If you're getting that voltage, you're basically running at, well, I guess when you're running at your standard voltage up above, that's when you're kind of getting your 100% efficiency. So sometimes what we'll say is our efficiency will be equal to the E over kind of maybe I should, so this might be a little confusing, but so above, we're still under equilibrium conditions, right? So, so we'll maybe say at equilibrium, because you can see that, you could have a cell just not with different concentrations, and it'll affect your voltage, right? So it's like, you don't want to say just the standard conditions. You want to say what are like at the standard conditions for your cell, which is this equilibrium voltage. So so what you're going to say is the efficiency of your system is going to be the voltage you operate over this equilibrium. And so any like inefficiencies you have in your system will typically show up as losses in voltage. And so what we typically look at is something called overpotential. So these are differences in the voltage from what you would expect at equilibrium. So your overpotential is going to be like E minus your kind of E at equilibrium. And we're going to use this symbol the symbol eta. And so, and you might see this some places, you might see these with knots. You can also see these with E naught, and then they just lump this term, and then they'll just lump this term basically of the voltage, which is like the other term for the equilibrium voltage, because this is, we're still under equilibrium. So you might see them lump that term as an overpotential. So that's like the only difference. Kind of like, you know, it's just a matter of book. It's basically just bookkeeping. So keep in mind, this is not an efficiency. I know this is like for engineering, this is a really common efficiency symbol, but this is not an efficiency. All right, so there's 3 losses. So whenever I'm running an electrochemical system, I'm kind of curious, what are these 3 losses and which ones are dominant? And so the one that's pretty much always there are kinetic losses, right? So this involves getting your reactants to kind of what you call an activated state before they can get to the B products. And so there's usually an energetic barrier there that's going to decrease the efficiency of your cell. And so the reason why this is the first one I'm going to do is because these are usually the large compared to the other. They happen near equilibrium. So even small departures from equilibrium, these are present. They're hard to get rid of. Like the other ones, as an engineer, we can engineer them out. These ones are very hard to engineer out. And for like well-developed systems, this is usually one of the main focuses for developed systems. Because usually you've engineered out the other losses, and this is the one you're really limited by. Developed systems.
So what would some examples of kinetic losses be in a chemical system? It'd be like heat, for example.
Yep. So I mean, it's a great point. Like, where is this energy going, right? Your intuition is like energy is conserved. All these losses are going to show up as heat. So so if you have some, let's say if you have some current flowing, right? Like ideally you should be getting, in terms of the power, you should be getting your equilibrium voltage times your current, but you're not. You're getting the actual voltage. So actually I times your overpotential is going to be power as turned into heat. So inside your cell somewhere, this whatever current you're running at times this overpotential is going to be associated with the heat generation. Yeah. So actually, so it's interesting. So like fuel cells, right? We were talking about fuel cells for a while. I'm going to go back to fuel cells here. We kind of took a little divergence, but they produce water. And imagine if you're in, a place that goes below freezing and you're producing water on your reaction sites, it turns into ice, right? And then you have no more reaction sites. You can't get the oxygen to the reaction sites anymore. We didn't talk about, I don't know, maybe in diffusion, I'll find a way to talk about 3-phase boundaries, but you have specific reaction sites. And so what they'd actually do is you'd actually run your cell very inefficiently. You'd run it at an operating point where it's very inefficient. So you have high overpotentials. So you get a bunch of waste heat early on until you can heat up the whole cell. Because if you get ice covering all of your reaction sites before you heat up your cell dies. And so the goal was you'd operate in this mode that was as wasteful as possible, or maybe just at the point where you could heat up your cell before you filled up all of your reaction sites. So actually thinking about the heat in practical systems is actually pretty important. And you imagine like batteries, for example, the whole thermal management is a whole thing, right? So it all turns into heat. So, why don't we take? I'm gonna top off my coffee. Give me like a 3-minute break, or bathroom break, and we'll be back. And we'll be back. You take a stretch break, bathroom break too. See how many? Let's see how many people we got here. Maya, Damien. Oh, we got Arnaldo. Oh, wait, no more. I don't see one from Shen's group. So am I going too fast on this stuff, or am I going too slow? What do people prefer?
No, that's good. It's good pace.
You keeping up?
Somewhat.
Yeah, I'm gonna have to go back and go through everything, but I mean, chemistry isn't really my strong suit yet, but it's a good pace.
We got our energy density. So let's get going on this. So there's a lot of theory involved in kinetics, but let's just start off at a high level to start. And kind of the most prevalently used theory to understand it is Butler-Volmer. It's called the Butler-Volmer equation. So it results, the theory results in this equation. I don't want to go too much into the theory today, just because it's pretty involved. But their basic premise is that if you have some current over area, so you have some like current density, and we'll say that's equal to J naught, then this is, oh sorry, not J naught, it's gonna be equal to J. This is gonna be equal to some J naught, which is our exchange current density, times you're going to have exponent of an alpha times f times, we've been using n in this class so far, n over RT times the overpotential minus the exponent of negative, and this is usually a 1 minus alpha fn. So this is 1 minus alpha over RT times the overpotential. Sometimes you'll see there'll be some like concentrations here, but usually we'll assume these are 1. And this alpha, so what you basically have here is you have a forward reaction and a backwards reaction. And so you imagine you have your products here, and you have your reactants have an energy here. So this is like energy, and so this is the equilibrium energy of your products. So your reactants. This is the equilibrium energy of your products, right? And they need to go to get to your products. They need to first like reorient themselves and get to a place where they can turn into their products. And so you have this activation barrier. So you have this activation barrier. And products can go turn back into reactants, and reactants can turn into products, right? And so I drew this like a pie here, and so that the activation barrier for the products is much higher than the activation here is much higher for the products than it is for the to go back to reactants. And so this will mostly go in one direction. But so this is basically, you're saying there's some current going to the left, some reactions going to the left, some reactions going to the right, and it's associated with this barrier. And so this alpha term kind of describes the shape of the profiles, but we're going to just say alpha is 0.5 for our case. And a lot of times what we're going to say is that we can ignore the backwards. So sometimes you'll just say there's a large overpotential, so large overpotential, so doesn't go backwards. So that's probably true here. But if you had some situation, which was, it's probably a reasonable, but if you had something more like this, right, where the relative barriers, where the relative barriers were more equal to each other, then you would want to include the forward and backwards reaction. But so we're going to ignore this term. And so what we're going to basically say is that our current is equal to our exchange current density, which I should say our exchange current density. So that's basically, if you're at equilibrium, let's say they're here and here. The exchange current density is basically how quickly do they go here. Some are going this way and some are going that way, and they're equal. But this is your J naught. So they're actually going to be going back and forth, but at equal rates. So this J naught is going to be Faraday's constant times K naught. And so this is actually what you need to look up. So this is the standard reaction, right? So you need to look, this is usually found from experiments. Right, and it's going to be multiplied by the concentration. Let's see here, of your reactant to the power of alpha times the concentrations of your product to the power of alpha. So you're going to have these, well, I should say 1 minus alpha, just in case it goes. In case you're using an alpha that's not 0.5, but you can see how if alpha is 0.5, then both of those will be the same number. So you have J equals J naught, and then we have the exponent of alpha F N over RT times this overpotential. And so typically we'll solve for the overpotential. So we'll solve for the overpotential, and so we'll have to divide this over. So we'll have a current density, current per area, times J naught, and we're going to have the natural log of this term, and this is going to be times RT over alpha Fn. And this is called the Tafel equation. Tafel equation. And this is for large overpotentials. Right, and so you'll see this number here, 3.4 times 298 divided by 0.5. So our n in this case is equal to 2 divided by 9.645. So in this case, this term right here is going to be equal to 25 millivolts. So that's a really common number you'll see in electrochemistry come up over and over again. Is this 25 millivolts? And then the question is what is the, and so what this kind of looks like on a, let's say you only had losses from this. So if you looked at this, if you took the natural log of your current density and plotted it versus your overpotential in an experiment, what you'd see is it would be, it'll be kind of linear early on, but then it'll flatten out. So these large overpotentials, when you fit this data, it looks kind of linear. And so this is going to be this the slope, right? It'll be alpha F N over RT, right? And then this, where it hits here, that's going to be your exchange current density. So this will be your J naught. Right, so typically this is how you get the data. You'd run an experiment and you'd measure the current. So this is the current. You just divide it by area and then take the natural log of it. And this would be your voltage minus the equilibrium voltage. So you make this plot and then you'd fit this data here. And so what's basically been found for platinum and fuel cells. So this J naught for platinum for the hydrogen side of the fuel cell is like 5 times 10 to the negative 4 amps per centimeter squared. And for O2, it's like 5 times 10 to the negative 8 amps per centimeter squared. Right, and so the exchange current density is much lower for the oxygen side, which means it's much harder reaction to get going. And so, like, where do you think we put more of our platinum? Do we put it more on the hydrogen side of the fuel cell or more on the oxygen side of the fuel cell? You know, it's not cheap, so you don't want to waste it. So you should put more of your catalyst where it's slow or more of your catalyst where it's fast. So this is the slow reaction. This is your fast reaction in the fuel cell. Where do you think you put more of a catalyst to help speed up?
On the oxygen side?
Yeah, right. Like your oxygen's really limiting you, right? And so you need to put it here. So put it here. All right, so let's fire up if you have your old code from last time, we can fire it up. So let's see here. Is it on my desktop still? No. Put it in. Yeah, we got our electrochemistry workshop. We have our. So yesterday we were working on more of a. Today we worked a little bit on an iron chrome system, but we're also last time we were working a lot more on the fuel cell. So so this is E3 in my code is the one with the curve fit. So here we're going to plot. So this will be where we take into account our kinetic losses. Right? And so our over potential, so I'll just call this like eta, because that's that symbol for over potential. Eta kin, so that's our over potential due to our kinetics. It's going to be equal to I just said was going to be this Tafel equation, right? So we're going to have R times T I don't think I have R in here yet. R is equal to 8.314 just kilojoules per mole Kelvin. So we have R times T divided by, in this case, I don't know if we have an alpha yet. So we'll have our alpha times our N times our F, right, times log we also of J, and we'll do everything in current density. Was we can do J divided by J naught. So we need to give it a J naught. So J naught is going to be equal to, so let's do the slower reaction, right? So that was, so J naught was, let's go back, it was 5 times 10 to the negative 8. 5e to the negative 8. And we're going to have to make a vector for J. So we'll go J from, it's equal to a vector from 0 current by 1 e to the negative 3 all the way to current of 1. So this is current in amp per centimeter squared. This was exchange current density in amp per centimeter squared. So, and then we're gonna have to do J divided by J naught. So I think log, get a multiplication symbol here. And then we can say that so our voltage from kinetics with just kinetic losses will be E3 minus eta kin. And then we're going to want to plot our J versus our voltage associated with kinetics. Sorry, one sec. My computer disconnected. I could tell from the internet again. Right, I'm back. Okay, so what I have here, right, is I have my alpha, I have my exchange current density. Go away. My exchange current density, right? And then I make a vector, just a vector from 0 to 1, so that I can help plot for different currents what the voltage will be. And then here I'm calculating the eta, so that's over potential kinetic, RT divided by alpha. I take the log, and then I calculate what will be the voltage with just the kinetic losses, and I'm going to plot it. So let's find the bugs. So you can see in this case, up to current densities that are this large, we almost can't go anywhere near that voltage, right? We're dropping like flies. So what we do in this case is we make the surface area on our catalyst. So let's say so what we do to solve this problem, right? Because you can see like we can't get any voltage out of our fuel cell now with this losses. So what we have to do is we might have, let's say 10 centimeters by 10 centimeters of fuel cell. But what we're going to do is we're going to load it up with a ton of catalyst. So this will be like high surface area catalyst. So that it has, you know, maybe on the order of 1,000 times higher surface area, you know. So let's see here. I found a value in this book for after they do this. I know is so it's around like 7 even -5. So after they do this, after you do this, you can kind of effectively increase this value for your cell because it's not seeing the same currents. You know, the actual like where the kinetics are happening actually are not seeing very as high of currents as the other one. And so what you could or let's go back. It's easy. So we could say loading ratio. So we'll do LR, loading ratio. And so maybe this is 1,000. So we call that other area the active area in the cell. So that means we can divide this. That means we can divide this current density by 1,000 because it's actually 1,000 times lower when we're calculating the kinetics. So let's calculate the kinetics now. All right, so this is a little bit more reasonable, but you can see. So if I did 1,000, that's going to get me down to alpha n. So surprised how high these are. So let's say if we could load it up 10,000 times. All right, so now, but you can see why kinetics, they kill your battery even at extremely low currents, right? So this is on an amp per centimeter squared. And so they happen right away, which makes them really annoying because they're going to kill your cell right away. So it's going to go 100,000 times the surface area. So you know, we're putting in a ton of super high surface area. So here we can begin to get some of this voltage that we were hoping for. So you can see if you can keep increasing the area, you can start to get some some reasonable, and because here, right, our 1.2, so even at a small current, right, 0.2, it'll look like this. All right, so those are the kinetic losses. And so this ended up being 1, 2, 3, 4, 5, 6. So this was 1,000,000, 1e⁶, in order to really get these, if you want to really get them down. But then that's going to be a really expensive fuel cell. Or maybe you just hope you have a lot better catalyst than platinum, and that's your other hope. All right, so let's move on to the next other things that are going to cause. So you also have resistance losses. So you can usually design these out. But there are advanced systems. So like a lot of systems, this is kind of designed out. They figured it out, but there's also a lot of newer systems where they're still trying to find out how you can get that out. And so the overpotential here associated with resistance, it's just going to be equal to kind of your common J times R. This is what we call this the area specific resistance. Right, and so this is going to have units of like ohms per centimeter squared. And so this R, so this R can come from the membrane, like your membrane might have some resistance to it. It can come from the solution resistance. It can come from connections in your system, right? They'll all play in there. I don't know, rough good one for a fuel cell is maybe on the order of 30 times 10 to the negative 6. Or let's just say, sorry, 30 times 10 to the negative 3. I was going to do it in kilo ohms per centimeter squared. You could also, so you kind of know for some sort of kind of like area, so it says cross-sectional area A, you had electrodes on both sides, and this has some conductivity. So it's supposed to be a sigma for conductivity. That the resistance is going to be equal to, it's going to get larger as the length of this gets longer, and the resistance is going to go down as the conductivity increases and as the area increases. And so, so this term right here, let's see here. This term right here is kind of, this is your like area specific resistance. Right. So or let's say area specific resistance, or I mean more specific, it's 1 over it. Right. So so at this point, and if you basically if you had the conductivity, you could figure out what your area specific resistance is, right? So your area, so R, right? It's going to increase with length and decrease with conductivity. So if you knew the conductivity of your membrane and you knew how thick it was, so this is our thickness, you could find this value. But we can basically use this. So let's go back into our code and let's try and include that now. So we're gonna include resistance losses. So our R is going to be equal to 30 e to the negative 3, and that's going to be in ohms per centimeter squared. Right? And so our eta for resistance is going to be equal to our, it's going to be equal to J times R. Right? And so we can get rid of this part. And let's include these two. So now our voltage will do minus eta resistance. So we plot just our E. Let's see how this looks. And so what you'll see now, so before, and maybe we could let's do, we could keep this on. So E can, and this will be, we'll do hold on. So that'll keep it from over plotting it. So you see, so before it just kind of will come and it'll start to flatten out. So we can increase it to higher. So let's go up to 10. Right, and so you'll see that from the kinetic losses, it'll kind of flatten out, and you'll start to not have as much losses from. But you add this kind of linear slope onto this, and that's why it gets linear down here, because these are your resistance losses down in here. Does everyone kind of see that? How these different losses are coming into play in your system? All right, so let's go to the last one I want to talk about today, are our diffusion losses. So these are the three. We usually think about kinetics, resistance, and diffusion losses. Sometimes they call this concentration polarization. Right, and so this is losses associated with not getting reactants to reaction sites, or getting products away. And so we've kind of seen from the Nernst equation that you have some change in voltage associated with RT over NF natural log the concentration of your reactants over the concentration of your products, right? So we see, but before we were just including the bulk, but actually you need to know what that is right at the surface of the reaction site. So it needs to be at the site. So for example, talk about like 3 phase boundaries in some of these systems. right? So that's this point here. So basically in a fuel cell, right, on the oxygen side, we need oxygen to be there. We need our proton conductor with protons. And we need our electron conductor. And where all three of these meet, this can react. They can all react together, right? And out can come water. But one like geometric issue is you can't really make like it's hard, like you can't really make a continuous like three-phase boundary. Like, so you need something. This is like just space for oxygen. This is like your electronic conductor. So this is like your GDL or your carbon felt or your catalyst. And you need this proton conductor. You also need your membrane there. This is like your membrane. So these are your only real reaction sites. So that's also just an interesting, how do you get a good three-phase boundary in your system? Because otherwise you just don't have very many reaction sites, right? Because you need to be able to get all those things to the exact same location for that reaction. But so what we kind of think about here is that the concentration of our reactants, if we start having this reaction happen really, really fast, at some point our reactants aren't going to have, we won't have any reactants there anymore. We can't get them there fast enough to react. So imagine like you're flowing in your cell 10 atoms, per second. If you're reacting 10 atoms per second, there's just not going to be any more reactants there. And so this concentration will drop. And so it usually follows some form like this, 1 minus I over I limiting. Maya is going to help us like actually track all this stuff, but this is how you might track it at kind of a high level. So once I approaches IL, the concentration of your reactants approaches zero basically, right? And so if we put this into this, so we divide these both by the, and if you're not doing any reaction, so if I approaches zero, then basically the concentration of your products go to zero, right? And so that thing goes to infinite, right? If you're not doing any reactions, you don't have any products, so your concentration of your product is zero. So our overpotential from diffusion and getting things to the reaction site, we'll usually model as, again, we have this RT over NF term, you'll kind of notice keep popping up, times 1 minus, and we should probably use J here. So we'll typically, and this time we'll typically use current densities, J over J limiting, right? We'll say, J limiting for fuel cells, it's getting better and better. Because you can usually engineer these, right? It's just, this is about like literally just kind of getting reactants there. So for fuel cells, it's going to be on the order of like 2 to 3 amps per centimeter squared these days, right? So let's plug in our last one. So this is our diffusion losses, right? And so here we need our I sub L, our limiting current, right? And we said this was, let's put like 3, and that's gonna be amps per centimeter squared. So limiting,
It's not showing up on your screen. It's still the previous screen.
yeah, thanks. Sorry about that. It's funny, it's like it's just this computer, my work computer, just like drops its internet connection for some reason. Sorry about that. But so this is limiting current, right? And this is an amps per centimeter squared. And we said, so our eta, our overpotential for diffusion in this case, is going to be R times T divided by N times F times log of 1 minus we were using J. Sorry, I'm gonna switch from I to J. Some people use J, some people use I. So J divided by J L, and we're gonna need to, I believe, do a dot here because it's JL, because J here is a maybe not. Let's try it without. And I'm gonna have this go to 5 roughly. I think will be enough. So I'm gonna have my current density go from 0 to 5, and then so this will be we can just get, we'll do the sum. Oh, just keep adding. So this one I'm going to get rid of the kinetics from it. I'm just going to call this E resistance and E resistance. And this one I'm going to subtract. I'm going to do minus eta diffusion losses. And I think that could get us there. So but we're going to need to hold on. So you see our over potential losses. Let's see. I think I might need a minus sign. Am I missing a minus sign? Let's really say the thing one time. Yeah, I think that there should be a minus sign here. Because so the reason for the minus sign is because we've defined our, so this term, we've basically defined our overpotentials as E minus E equilibrium. And so because of that, there should be a minus sign on this one actually. That's again just kind of a bookkeeping thing, but you just want to make sure you get it right. There we go. So what you'll see is that, so if we look at, and maybe I can also plot just the diffusion losses. So eta diffusion. So we'll do one of these. So we'll have E diffusion, and I'll just subtract eta diffusion, and we'll do E diffusion. So does anyone know is it just like x-axis? And then you say like current density. Forget the nomenclature.
I think it's X label.
X label, thank you. Y label is going to be our voltage. Our legend equal. So this is, I think it's what we started with. Kinetic losses, resistance losses, diffusion losses. And now we have our cell voltage. Fix it in terms of what Jose told me. We got our X label. All right, let's find all my errors. And so let's do, And I think I have to do, what do I have to do? I have to do legend on or something. Oh, is that the right syntax for this? The legend syntax.
For legend, you don't need to put equals. You just put, and then a parentheses instead of brackets.
Thank you, Jose. All right. So we can see the individual ones. So the kinetic losses, you see why they're so huge right off the bat, basically. Is they're going to start to drop. And let's check what temperature was I running this cell at this whole time. It's at 1,000. Let's run that room temperature. Okay, there we go. That looks better. All right, so here's like our equilibrium voltage right here. And then the purple is our cell voltage. And so what you're gonna see, right, is you're gonna have kind of immediate. Let's see here. Our kinetic losses probably aren't as high as they should be. So we've probably made this. This should probably be -4 or something. I thought we were operating at room temperature last time. And then I think there's one issue with our diffusion. E diffusion minus RT. Okay, so this looks right actually. So this actually goes all the way down to 0. It's just not tracking it super well, but it's actually, after this point, it's going to die. It doesn't have this backup. So the cell is dead after 3 amps per centimeter squared, because that's your limiting current. And so what you can see is these 3 contributions. Like you have this initial big drop from kinetics, right? So initially the voltage basically follows the kinetics. And then you start to follow more of this linear slope of the resistance, right? And then you have this cell dying here around 3. So I'm just going to run it to 3 so it looks better. 3, and we can make a little higher resolution. Go to 1e-4. Right? And so we can do edit, copy figure, bring this into our notes now. So yeah, so you can see like early on, kind of like we suggested, right? This is like, this early stage is dominated by kinetics, right? And then you have this phase, which the slope is basically like this resistance. So this is resistance dominant. And then you have this diffusion losses down in here. So if you wanted to, we could also plot. So we could also plot the power of the system, right? So so cell so we'll just do a new figure. So power is going to be equal to E times J, right, at every point. And so then we're going to, and this will be in, this power is going to be in watts per centimeter squared. So, so we're going to do a new figure. And we're going to do a similar plot. Right. And so for now, instead of E, we're going to plot power. This is going to be power density. Let's try plotting that. So I messed up the, it's supposed to be lowercase p. Why not? So this one's, whoops, I did the, so you can see here that the power in this case, because the voltages are so high, our power, we're getting a peak power close to our limiting current density. And that's a little bit further to the side than I was going to expect. Let me see this. RT over NF log, that looks good. Let me make sure this function is strong enough. R times T divided by N divided by F. 12. Okay, well, it is what it is. I'd probably expect you might have some factor in here. You'll find some people will kind of use a fudge factor here to fit their experimental data. You'll see, the hump won't be so sharp anymore, basically. It's because, and so, okay, so here, yeah, here you'll see a little bit better. So, and I need a, so you see kind of, here's the power density, right? So you meet your peak power here, but you actually, your highest efficiency is when you're at your highest voltage right here. So typically you're going to operate somewhere in the middle of these two, so you get a good balance of power and energy density. Jose, do you know how to limit the X scales? So this one should still be current density.
Yeah, you put X limit or X lim.
So Y lim, and then can I say like 0 to whatever the normal bound is, or no? 0 to,
I think it does it by
two numbers. Like,
by
can I have it
ticks.
still automatically do the upper bound? Or no?
I don't know about that one.
So I just don't want, it doesn't make sense to go below.
Yeah.
This is watt per centimeter squared. That's good. So we're getting up to about 1.5 watts per centimeter squared. Not bad. Pretty good. So that looks good. And so the other one I want to Y lim this to was it, like 2? That looks better. Okay, so I think we got our kind of first high level modeling. And so you can see, like, let's say you want to do some high level modeling of your system. These would be kind of the highest level parameters you could think about trying to get for your cell. These are pretty high. Some like the limiting current, right? It's like it's so high level, it's hard to get it from like just a diffusion coefficient. But we'll talk about how to calculate those a little bit more precisely with Maya next week. The other thing now you can do, and so between now and next week, what a little bit of homework you can do is one, find some papers modeling your system. Right, and see if you can kind of figure out, and they're going to do more active probably tracking of all the species in the system, like we're going to start doing. But see if you can start to find all the over potentials. See if you could start to figure out some of these parameters. Even you could even think to start to fit some of their data. You know, you could even, if you had a similar system, you could take their data and then try and manipulate these values to fit their data, and you could probably get it those ways. And 2, if you're doing a flow battery, what you're going to have is you're going to have a combination of the 2 things we did today, right? So the first thing we did was we looked at the state of charge, right? We looked at this kind of voltage versus state of charge. But you could also, if you did this at a constant current, you could figure out what should my over potential be. So you could go the total over potential from the other code and figure, okay, so I'm not actually here. So let's want to put so this is so X label. Let's go to our other. So here, in this case, it's state of charge. And this is equilibrium voltage. All right, so let's edit figure. So for the flow battery folks, what you could do is you could try and produce something like this, but you could say, okay, well, I'm going to look at, you know, maybe a couple different current densities, and you could see, okay, well, if this value right here, 1.2 is or no, must be right here, is the equilibrium voltage right here, 1.22. Here is going to be my loss all the way, you know, down to 1. So maybe that's 0.22. And so as you ran the cell, you'd have a constant offset in your voltage during the discharge curve. And so you could figure out, you could actually do some cool stuff. You could figure, so this would be your actual, so this would be V actual now. This would be your actual kind of voltage. And you could figure out what's my actual energy density, right? So we integrated that before to get energy density. So you get energy density actual. And you can actually make a really cool plot. So a cool plot we like to think about is, for your cell, is the power density over the energy density. So right, you could come from up from this first part. You come up from this first part, and you could say, okay, what was my power density, right? Because we already calculated the power density at this specific point, right? So you do this for multiple points. You go and you do it for like here, 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 here for your system. And then you'd go into your power density. Right, so we have to go back into this code. Then you say, okay, well, at those figure. Right, and so should say is that. So you'd say, okay, you take this, you'd run, you basically everything for this point, and you'd say, okay, I'm going to get the over potential. So this is eta at 0.1, so this is 0.1, and then I'd get, this is the power at 0.1, and then for that eta at 0.1, you could run your model. So this is eta 1, and you could get from this integral, you could get the energy at condition 1. And so you have energy density and you'd have power density. And what you'd see is that at really low power densities, at low currents, you're going to get the highest energy density. And as you go higher and higher, you're going to start to lose energy density until you're going to reach some plateau. So you typically get curves that look like this. And this is actually called a Ragone plot. And we compare a lot of technologies on these. And you obviously want to push this direction. This is what you want. You want high energy densities and high power densities. But it's kind of a nice plot to show what's the trade-off for your system in terms of power density. So if you want to run high power, you're going to get low energy. So this is power high, your energy density is low. Or you might run in a scenario where your power is low, but you want high energy density, depending on what you need. So even with these kind of simple models, you can begin to kind of make some assessment about this technology, and there'll be, you could compare it. You're going to have like, capacitors are up here, right? Batteries are down here. Fuel cells are kind of somewhere in the middle. Somewhere's fuel cells. Fuel cells are a little bit weird in that they don't really have an energy density. It kind of depends on their tank. But I think so they're probably actually somewhere down here with down closer here to the batteries in terms of that. Actually, they're probably pretty close to each other. So you could start to compare it for different technologies. So let's see here. Maybe we can find a good. Let's see here. So let's get the real. So here you can see. So here you have here you have energy and power, right? So you have these capacitors are super high, right? The batteries, internal combustion engines. So the fuel cells with a really big tank, they're even pushed out here a little bit, right? Gasoline cars. So you can see how it's a kind of a nice way to compare all the different technologies that are out there. So you could take your system and you could plot it on this, and you can see, how do you compare? How does your system compare as an energy technology? So these fuel cells, we got to push them down a little bit. Not that I had any axes on here actually, but roughly. Okay, so I think once you have this too, I think it'll, when we go into some of the more detailed stuff, you'll kind of understand we're basically just trying to get at what are the diffusion losses, what are the resistance losses, right? What are the kinetic losses in our system, right? And so we're just trying to, and what is at the very start, right, was kind of what is the equilibrium? What is kind of the equilibrium if we just went super slow and didn't have any losses, right? So once you can kind of get these aspects, and the more you can go, your model can go all the way down to the Schrodinger equation, to try and get the details of these. But those are kind of at a high level what we're trying to find when we're doing this. Yeah, so I think with that, if there's not any questions, we're already a little over on time for folks. So we got Jose, we got Arnaldo. So I think we'll plan to meet next Tuesday.